Assalamu alaikum and welcome back. We often see in movies and such that someone enters a portal and ends up somewhere 200 years in the past, or someone goes into a portal and ends up 3 or 4,000 years in the future, and the time has changed or time has moved far ahead, or he goes back into his own past. These things might sound completely unbelievable, like how could it possibly be true for you to leave one specific time and then enter another distinct time? But the crucial thing to consider here is that a significant part of this concept is actually quite true, and in fact scientifically and demonstrably possible. We really can have a slight yet measurable effect on the passage of time. We can actually go slightly into the future. In physics, this concept is called time dilation, and it comes from Einstein's most famous theory, relativity. When we talked about gravity, we saw how it slightly bends the fabric of space-time. We visualized this and saw how planets revolve around the sun and why they don't fall into the sun. The fabric that was being bent is not just the fabric of space, but also of time. It can be bent. So if there is a planet in space or a star within space, it not only bends the fabric of gravity, but also the fabric of time. This is a scientific phenomenon with complete mathematical reasoning behind it. If one person is on Earth and his friend is far away from Earth, where gravity is much weaker, the person on Earth will experience time passing slightly more slowly, while for the one far away, time will pass a bit faster. We can't observe this phenomenon directly because the change is extremely tiny, almost minuscule, so we've never visually observed it. Instead, scientists have special clocks called atomic clocks for this purpose. When they tested this theory, they found that it was absolutely perfect, and indeed, time passes a little more slowly if you are in a weaker gravitational field, and it passes faster if you are in a stronger gravitational field. There are many planets. Jupiter, for example, is a very large planet with a huge mass. The greater the mass, the stronger the gravity. If you were on its surface, you wouldn't be able to stand. You would fall to the ground and wouldn't even be able to sit because the gravity is so intense there. On Earth it's fine, you can stand here. So if you take a clock and leave it on Earth and take another clock and put it on Jupiter, after many years when you come back and compare the two clocks, you'll find that the clock on Jupiter runs slightly slower, while the clock on Earth runs a bit faster. Now here on Earth we can't see that difference in our clocks, but if you check the same clock on Jupiter, you'll realize that less time has passed there. This is called time dilation, and Einstein proved this in his equations, that this is exactly how it works. Now, you might be wondering, what's the point of studying such tiny effects? Why did scientists even think about this, especially if the effect is so small, and if we can't travel hundreds of years into the past or see the future centuries ahead, then what's the practical use of this discovery? The benefit is that the satellites above us are in a weaker gravitational field, while we, who receive data from them, are in a stronger gravitational field. This creates a slight time difference that we have to account for. That's why the clocks on those satellites and the clocks on Earth don't stay synchronized. Time starts running a bit faster on the satellites and a bit slower on Earth. To correct this, scientists constantly have to adjust the time, just like when we're at home and our clock is a little off, so we set it 5 minutes forward or backward. Similarly, even incredibly precise atomic clocks, which are designed not to malfunction or lose time, have to be meticulously adjusted by dedicated scientists. They frequently have to set them back by a very tiny, almost imperceptible amount of time. So, for scientists who are stationed on the International Space Station, their chronological age can differ significantly from ours by a minuscule 0.002 seconds, if they spend an extended period of 6 or even 10 months up there in orbit and then eventually return to Earth. They have experienced a distinctly different passage of time than we have. Their fundamental concept of time was inherently different from ours because they were experiencing the flow of time in a profoundly different way, and we were experiencing it in another, more conventional manner. This phenomenon doesn't happen just because of the effects of gravity. You can also experience this remarkable temporal dilation due to high speed, and this intriguing concept is thoroughly explained by the principles of special relativity in much the same comprehensive way as we meticulously explained gravity's profound effect on time. Special relativity explicitly states that you can experience exactly the same temporal phenomenon by moving significantly faster or considerably slower through space-time. To experience this, you have to travel at the speed of light or get very close to it, and as we discussed in the first episode, the speed of light is not a slow speed at all. The speed of light is extremely fast. If it can reach the moon in just 1 second, then humans can't even begin to imagine experiencing that speed. So we can only observe this in theory, that if we were to travel that fast, time would pass a little more slowly for us. It's hard for us to fully grasp this because it's a very difficult concept to understand. Relativity is not an easy subject because it completely changed our view of the universe. The way we used to think the universe was simple, relativity showed us that it's not that simple, and the universe is actually a bit more complicated. Now, when it comes to understanding just how strange and unique the speed of light is and how it behaves, let me explain it to you. Imagine you're standing on a road and a car passes by you at a very high speed. Let's say you're on the motorway and a car passes in front of you at 100 kilometers per hour. Naturally, as you're standing there watching, you'll say, this car just passed by at 100 kilometers per hour. Now, if you also get into a car and you're driving at 50 kilometers per hour, so when you look at it, you'll say it's going at 50 because now your speed has become accustomed to its speed. If you are also going at 100 kilometers per hour and the car in front of you is also going at 100 kilometers per hour, then when you look at it, you'll say it's not moving at all, it's right alongside me. So, to calculate the relative speed, you subtract the speed of your own car from that of the other, and that's how you get the relative speed. The incredible speed of light is so profoundly strange that it simply doesn't follow this particular fundamental law of physics. Suppose for a moment you were to get hold of a truly remarkable space rocket that is capable of traveling at an astonishing 50% the speed of light. Alright, so now you're also traveling at half the speed of light, and if that same laser beam passes by in front of you, you'd look at it and say, now it's going at half the speed of light, it's going at 50% the speed of light. Right? That's what you'd say, wouldn't you? If you were traveling at 90% the speed of light in your spaceship and a laser beam passed by in front of you, you'd look at it and say, it's going at 10% the speed of light. But actually, that's not what happens. No matter how fast you go, it will always pass by you at the same speed. Even if you stand still, it passes by at the speed of light. If you move at half its speed, it still passes by at the speed of light. If you move at 99% of its speed, it will still pass you just as quickly. In fact, with a car, we saw that the faster you go, the more it seems to stop and move along with you. But that's not the case with light. With light, it's as if it knows how fast you're going and becomes just as much faster. This is the strange and fascinating thing about the speed of light. It's not relative, it's constant. No matter how fast you go, you will always see its speed as exactly what it is. This phenomenon was explained by scientists in special relativity when Albert Einstein introduced it. The formula he gave was so strong that we are still confirming it to this day. We keep proving it, and experiments continue to show that Einstein was indeed correct. There are even more astonishing things present in our universe, and we will understand them in more detail in the next episode. So, allow me to take my leave.